All right, let's get to it. Lecture number 3, I think. This is all about the solar system, so we're going to kind of jump around in the text a little bit. Some of chapter 7 and some of chapter 14. Let's do it. You might know a good bit of this stuff already, but I'm just going to kind of take inventory. What is in the solar system? At least the bigger things. So we got the sun in the center. The kind of lighter lines are the planets, the orbits of the planets, mostly circular, a little bit elliptical, like we talked about earlier, but still pretty close to circles. The red lines are some comets and dwarf planets, pretty elliptical orbits, or higher eccentricity, remember that word? And as it turns out, it's about 4.5 billion years old. So how is the mass distributed throughout the solar system, right? Where's all this stuff? The majority of the stuff is in the sun, almost all of it. Jupiter is the next closest, but only makes up 0.1%. And I don't know why these are in order like that, but the planets would be the next, 0.04, and then something like the comets and asteroids and the cosmic dust that surrounds the solar system. So if it turns out if you took away everything but the sun, it's basically the same mass of the solar system as it is now. If you took away everything but the sun and Jupiter, really close to being pretty much the same, at least as far as all the mass is concerned. And how do we know some of these things? Well, a number of different ways, but one way by using Kepler's third law, or maybe the modified version that Newton had. If you remember, related the area of the orbits and their period, and then Newton came along and modified it and has the masses in there as well. So we can measure the area of the orbit by seeing how far around it is, and then can measure the period pretty easily, how long it takes to get around, so we can pull out some of the mass information there. Besides that, we have Newton's law of gravity, or understanding of gravity and the way things pull on each other, and we have formulas that allow us to actually calculate the masses of things depending on how they're actually pulling on each other. So we use that, like how the planets pull on each other, or how their orbits are adjusted a little bit due to the gravitational pull of the other planets and the moons, and then even when we fly spacecraft by some of these planets, how they get pulled a little bit towards it, we can tell about the mass of those objects. So there's another picture of the solar system, definitely not distance-wise to scale. I'm not even sure if diameter, like how big they are relative to each other, the planets is. It looks fairly close. Right? The sun, very big. Jupiter, next sort of thing. Saturn, Uranus, and Neptune are pretty close together. The Earth and Venus, actually very similar sizes. Mars is fairly small. Mercury is fairly small. Yeah, so the sizes is probably pretty good, just not the distances. So when we talk about the solar system, often we'll split it into two areas, so the inner and the outer solar system. So I put this red line, that red dashed line in there to indicate that's sort of the split, and it happens to be also where there's an asteroid belt, but there's a pretty big gap distance-wise after Mars to Jupiter. There's a fairly large gap in those size of those orbits. Right? So everything within there we call the inner planets, or sometimes called the terrestrial planets. And so the inner planets are mostly composed of rock, which is like silicates, silicon and oxygen compounds, and metal. The outer planets then, after Mars, starting with Jupiter, are also called the Jovian planets. I think Jovian is actually like another way of saying Jupiter in some way, maybe a different language or some kind of different version. So the outer ones are kind of known as the Jupiter planets in a way. I guess the inner ones are the terrestrial ones, which is kind of like the Earth planets. So you got the Earth planets and the Jupiter planets. So whereas the inner planets are mostly made up of rock and metal, the outer planets are mostly made up of ices and gases, a lot of hydrogen and helium. But the ices, not just water ice, but also CH4, I think is methane, and NH3, ammonia. And just interesting to point out, like Saturn we know has rings, they're very visible. It turns out all of the outer planets actually have rings, they're just very faint. Right? They're very light dust for most of them, and you don't see them very easily. So some numbers about the planets. Yeah, so maybe to point out at least that a common thing to do in astronomy is to use Earth as sort of like a standard in a way. And so I told you about the AU, the astronomical unit. That's the distance from the Earth to the Sun, technically the semi-major axis, Earth to the Sun, or that orbit. And then the revolutionary period, usually, where these are all put up in years, right? So the Earth, in both distance to the Sun and revolution period, is just one. It's a standard. So the other ones are kind of measured relative to that. And as you would expect from Kepler's law, Kepler's third law, I think, the period goes up as you get further out. It's longer to rotate around the further you are out. Yeah, I don't know, just look at some of the diameters here. Jupiter, obviously, is enormous. 142,000 kilometers across. Over 10 times the diameter of Earth. Right along with that, it's also the most massive, or it has the most mass, and those masses are times 10 to the 23rd kilograms. They're quite a lot of mass. But if you look at the density, Jupiter is actually not very dense compared to the inner planets. And one thing that ends up saying a lot about the planets is just their overall density, because that, along with like their size, can give us an indication pretty easily of like kind of stuff they're made of. So if their density is pretty large, then it's a pretty fair thing to say that they're probably more made up of like heavier things like metals and rocks, versus very pretty low density, mostly made up of like gases and ices. And as I'm sure you know, the Earth has a moon. Technically, the term is a satellite. It's any body that's orbiting the planet. So the moon is a satellite. We call it the moon. And it's kind of confusing because moon is also a general term. So all these other things are moons as well. But usually if we're talking about the moon, it's like the capital moon. It's our moon. But all the planets, except for Mercury and Venus, have moons. And some have quite a lot of them. Jupiter has quite a few. I'm not sure. Jupiter has at least like a dozen, or like 16 moons or something like that. We'll probably talk about it more later, but some of the moons are quite interesting because some of them I think maybe have liquid water. I think maybe Europa or Io actually is like a frozen moon, but it seems to have liquid water underneath that. And they also, some of them seem to also have volcanic activity, tectonic activity, and pretty active. So they're pretty interesting objects, some of these. And then sort of the rest of the stuff that's not really around the planets, they're not orbiting the planets, are asteroids, comets, and meteors. So if you remember in the past picture, there are these two sort of belts, or like rings of asteroids. I think the inner one's just called the asteroid belt, I think. And the outer one is called the Kuiper belt. So the outer one's like past Neptune, the inner one's in between Mars and Jupiter. Yeah, and so the asteroids are mostly rocky things, and maybe metals, like pretty solid, heavy things. That is as opposed to comets, right? The comets are mostly found outside of the outer planet Neptune, and they're very much lighter things. They're mostly like ice, made up of ices. And again, not just like water ice, but also like methane or ammonia. So there's just a couple of pictures, or some examples of an asteroid there, and a comet. And I guess, yeah, that asteroid we actually had sent a spacecraft to kind of survey and take pictures, and eventually landed on it in 2001. And in the comet picture, you can see this kind of gas, like vapor leaving. I think this picture is taken when it's closer to the sun, right? So most of the comets are pretty far out in the solar system, but they have orbits that sometimes will bring them close to the sun. And since they're made up of like ices, you get close to the sun, they start to turn to gas. And meteor, actually, I don't know, it's kind of an odd term, but it really has to do with like when some of this sorts of stuff makes it to the Earth, like starts to impact on the Earth, right? So if like pieces of these are breaking apart, smaller pieces or maybe slightly larger pieces, right? But either a comet or an asteroid comes in and actually penetrates into the Earth's atmosphere, then it's a meteor. That's what we call a meteor. It's like a thing from way out in outer space that's coming and going to the Earth's atmosphere. A lot of them tend to just burn up. They're not too large. They can't really make it through the atmosphere for vaporizing, and that's what we would call a shooting star, colloquially called a shooting star. But if one of those things actually makes it to the surface, impacts, that's called a meteorite. As I mentioned before, it's pretty hard to really grasp the scale of things that we talk about in astronomy. even thinking about the solar system, like almost unimaginably large. And that's just the solar system, right? The galaxy is far larger than that, and there's so many galaxies in the universe. So hopefully you watched that video, The Cosmic Voyage, and that gives you maybe a sense of the scale of the universe's size of things. I'm probably going to keep coming back around and trying to re-emphasize or give you another way of thinking about the scale of things in astronomy, right? Like the solar system. Maybe even in like elementary school or something, you made, or you know somebody who made like a model, little miniature model of the solar system. The thing is, most of those are almost never actually to scale, because if you shrink down the sun to something that's like this size, then the Earth is going to be like a speck of dust, and probably has to be very far away still in its orbit. People have made some pretty impressive efforts to actually make scale models, though. One of them is known as the Sweden solar system, so it's in Sweden, and the model actually goes throughout the whole country. So this model of the solar system is 1/20 millionth scale, or 1 to 20 million scale, meaning that it's 20 million times smaller than our actual solar system. So it's shrunk down, but it is to the same scale. The sun, the center of this solar system, is actually an arena. It was renamed in the last few years the Avicii Arena, and that's a picture of it. It's this big spherical arena, dome sort of thing. And it is 77 meters across. 77 meters, like 200, a little over 200 feet. Pretty large. And the picture on the right is a map of Sweden and showing where all the other planets sit in this scale model. And so the Earth and Mars and Mercury and Venus are actually fairly close as far as the whole country is concerned, right? They're still around, or they're still in the same city or the same province, at least, of the sun. I think Stockholm. But to be a little bit more specific, the Earth sits a little over 7.5 kilometers away from the sun in this scale model. And it is 65 centimeters across. So 65 centimeters, I don't know, like yay big, maybe a little bit bigger. It's about this big, and something maybe like 5 miles away. So if you make a scale model of the solar system, the sun is that big, the Earth is still only this big, and it's like 5 miles away. So yeah, you can look this up and see more of the details of it if you like. I just put one more on there to give you a sense of scale of the kind of the outer reaches, at least of the planets in the solar system, and that is that Neptune is all the way up here, which is 230 kilometers away, at least like 150 miles, 175 miles, maybe something like that. So the sun is that big, Neptune is 100, 200 miles away. And Neptune is about 2.5 meters across, which is maybe a bit taller than me. And even on here you can see some of the even further out things, Pluto, and then some of these other dwarf planets, I think, Eris. So the solar system is a pretty large thing. Now that we've sort of taken stock of what's in the solar system, let's talk a little bit about how it started. So those are very broad strokes of what happens. You have this sort of cloud of gas and dust that's just kind of in the galaxy, whirling around through the galaxy, and it gets dense enough where the stuff starts to get close enough together where gravity, or the gravitational pull between all this stuff, will start to sort of collapse it towards itself. And once you start that collapse, then we're on our way to starting a whole solar system. So this is just sort of like an artist's rendition of like what early solar system might look like. This solar nebula, right? This sort of cloud of dust and rocks forming, these larger and larger rocks forming. And this is a nice little animation of that whole process, right? It starts to collapse, and then things start to kind of clump together more and more and more, and then other things that are clumped together start clumping together. The larger clumps start clumping together, eventually start forming planets, and then finally the sun is collapsed enough that it ignites its nuclear core, and then sort of starts blowing the solar winds out and kind of pushes a lot of the extra debris still that's there away, and then we're pretty well on our way to having a solar system. So pretty brief, let's go into a little more detail. Oh, wait, before we go right into that, well, when astronomers think about how the solar system started, and try to make models, and in modern age make computer simulations and try to test out those models, see if their models actually give the correct sorts of things, right? Like, because the solar system is the way it is today, so we can look at it and see how it is, and then with our understanding of physics and chemistry and such, kind of make these models to say, okay, this is how I think it started, and you sort of play that out, and we need to get back to where we are now. So these are sort of the constraints that the way things are now puts on us, or sort of clues to say how things started. Three sort of main things that we're just going to think about a little bit, at least right here. As far as the motion, all the planets are orbiting in nearly the same plane. So they're all going around, basically, could be like on the same sort of disk. Mercury is like a little out of that compared to the rest of them, but it's only like 7 degrees out. Most of them are within a couple of degrees of the ecliptic, so that's like the plane that the Earth orbits in, right? But they're all pretty much orbiting the same plane and in the same orientation, going around. I think it's like clockwise. I'm not really sure. Looking down or looking up. They're all going in the same direction around. And all of them, except for Venus, revolve on their axis in the same direction, right? So the Earth, I always get that confused, right? The sun goes east to west, which means the Earth is revolving west to east, right? So we're kind of going this way, as are all the other planets except Venus. And I think we'll come back to that a little bit later. It's actually a very slow rotation too. Venus is the slowest in the solar system. And then like the age, right? We're able to date objects on Earth and like meteors that hit, meteorites, I guess then, like pieces of asteroids and comets that have landed on Earth, date those. We've been able to go to the moon and bring back pieces of the moon and date that. And there's other ways that the book talks about dating things too, having to do with like how many craters or the density of craters on planets. They do talk about radio dating or radioactive dating. It's a very interesting thing, but half-life and all that tends to confuse people, so we're not going to get too far into that. Needless to say that nothing that we've found seems to be any older than 4.5 billion years. So that's sort of like where we get our beginning of the solar system, or how old the solar system is. And even beyond that, most of the stuff that we've measured, or been able to measure, or pretty much all the stuff that we've been able to measure, seems to indicate that it sort of formed, or came together at least, in around like a few tens of millions of years in that sort of region. Like go for about 4.5 billion years back, and then within about 10 million years or so, or a couple 10 million years, pretty much everything was formed in that time. And then the last major thing is about sort of the chemical makeup of things, or the composition of the stuff. Very simply put, in the inner planets, or the terrestrial planets, they're pretty much rocks and metals. Like that's largely what composes the inner planets. The outer planets, largely ices and gas. So part of what astronomy does is try to figure out how do we get to here, right? With our understanding of physics, chemistry, what sort of models can we make that will actually arrive or agree with these constraints? And these are just very broad, kind of basic things, right? There's a lot more detailed observations that are made that need to still fit with your model, right? We're just talking about a very broad sort of picture. This then is a little bit more detailed look, or sort of breakdown of that progression that I showed you briefly 2 slides ago, where we have this solar nebula, right? This sort of cloud of gas and dust, a lot of hydrogen and helium, and then a little bit of some of the heavier elements. But once enough of it starts to kind of come together, then, like I said, gravity starts to pull all of this stuff. Everything's pulling on each other. All the things made out of matter are pulling each other together, and so it starts to contract. Not only is it contracting, it's also rotating. It's a much more natural state of things in general to not just be like super static and still. Things like to rotate, right? That's sort of more of a natural thing. And so all this gas and this dust is coming through the galaxy, and it's sort of swirling around all the other gas and dust there. And then again, once it gets like dense enough and enough of it starts to accumulate, then you start to get this sort of collapse that comes in, but it's swirling around, right? So we get this motion of this cloud that rotates around, and that rotation actually tends to sort of collapse in the upper, or like the poles, the top and the bottom of that swirl, and then flatten out the edges. You have to start to flatten out with this disk. Right? So we get a lot of the stuff collapsing into the center and then spreading out this sort of disk shape that's still swirling around. So in the disk, all that stuff that's swirling around, right, it's also attracted to each other, or to itself, to the other stuff in the disk gravitationally. So it sort of starts to clump together, and eventually you start to get larger and larger objects until we're finally at the scale of like kilometers, like a kilometer scale, or like a little less than a mile-ish. So like bits of dust and gas have collected together until we finally make these sort of larger objects. And that's what we start to call planetesimals, I believe is the term. And then basically those planetesimals, those like mile-ish scale objects now, will start to collide with other planetesimals and start to stick together. And once those are clumping together, then you pretty quickly start building up fairly large objects, which we then call protoplanets. And that's more the size of, I think, like a tenth the size of Earth, or roughly like the size of Mars. Right? That's where we start to call these the protoplanets. They're not quite planets yet, but they're really getting there. And I think that's probably what are indicated, those white things swirling around the disk in picture 3 there. And so those protoplanets then are still going to be picking up more of the planetesimals, and then possibly collisions between protoplanets. When you finally start to get to like planetary size, I think this process still takes like millions of years. But eventually, while that's all happening, all that stuff that collapsed down towards the center, like that's most of the mass of all that, of this cloud is collapsed into the center, shown really big here, smaller but still there. And that gravitational collapse is what leads to the sun, right? It collapses enough and heats up enough that it sparks nuclear fusion. And once we spark the sun going, it ignites and it will kind of like give like a, sort of like an explosion, and pushes initially, blows some stuff away. But then once it's going, once it's doing its nuclear fusion thing, then it actually settles into this like continuous flow where it's sending stuff away from the sun. All this stuff is kind of getting pushed from the sun, which is not just light, but it's like particles like protons and electrons, other things too. But we call that like the solar wind, right? So it's continually sort of blowing out from the center of our solar system, from the sun, and that sort of sweeps away a lot of the rest of the debris that's still floating around from all these planets accruing. And that debris ends up, for the most part, sort of coalescing into the belts, right? The rocky stuff doesn't get pushed out too far and eventually sort of puts into the asteroid belt or the Kuiper belt. The even lighter stuff, like the gaseous stuff, the ice, gets pushed out even further and ends up in these sort of clouds way outside of Neptune. I'm going to jump back really quick to that animation. So there you go. We got our dust cloud. It sort of collapses down. Those planetesimals start to form and they accrue together. And you get the protoplanets and then sort of planets, and the sun ignites and then sort of starts blowing all this stuff away. And in the end, we're pretty much left with the sun, the planets, and then that sort of excess debris at the asteroid belts and the icy clouds far outside the planets. That's the idea. I guess I maybe got a little ahead of myself. So this is mostly what I was saying, but written out, and maybe some more specific terms. Oh yeah, and then also a little bit why our inner and outer planets ended up being a bit different. Right, so with the inner planets, we got those sort of kilometer scale or like mile-ish scale rocky planetesimals that start to sort of clump together. The term for that is accretion. Right? And then they form protoplanets, like the size of Mars, or I guess Mercury as well, similar sizes. Oh, a little bit more detail here that I forgot as well. So once those planetesimals are colliding, pretty big things colliding, generates a lot of heat. And so that is generally enough to actually melt the material that these protoplanets are made of. Right? So they're rock and metals, but also lighter stuff, hydrogen and helium. But once the planets are melted, then you get this process called differentiation, where they differentiate. So the heavier elements like iron, nickel, right? Those things are heavier than, say, like helium and hydrogen. And so they will sort of tend to want to sink more towards the center of the planets, of the protoplanets. We end up with a lot of the metals more towards the center of these objects, these protoplanets, and outside of that is the next sort of heavier things like the silicates and rock and things like that. and then sort of on the very outside, whatever the very light stuff is, hydrogen and helium. But in the inner planets, they're relatively close to the sun compared to the size of the solar system. At least, like, remember in the Sweden model, right, all the inner planets are still sort of almost in the same city as the sun, right? And then Jupiter is a bit outside, but then it goes like, they get really far away pretty quickly. But those inner planets then, being that close to the sun, they get heated up quite a bit, and so these lighter elements like hydrogen and helium don't stick around as much in the inner solar system, right? It tends to get pushed away, or pushed out. So the formation of the outer planets then, pretty similar, except for the fact that the outer planets are further away, so they're sort of in the area where the gases that are getting pushed out of the inner solar system end up, and so they'll start to accrue more and more gas. Right? So they're still like rocky, metallic centers of these planets, but for most of their volume is made up of these gases. And actually, just like the sun, when the gases all start to coalesce into the planets, so like maybe Jupiter, they start to get pulled together by gravity and actually heats up. It turns out, I think, Jupiter is probably fairly close to actually igniting and being a second sun, fairly close to having a binary system. But Jupiter and none of the other gas planets, or the outer planets, were actually massive enough in order to squeeze enough to start that nuclear fusion, and so they eventually just sort of cool off and are left with mostly gas. And then, yeah, like I said, the sun ignites, starts blowing all this stuff away. Okay, so at this point, pretty nice idea. Hopefully it makes sense, and you can see how that all might sort of work out, at least very broadly speaking. But beyond that, we've been able to observe solar systems that are in the making. So look around our galaxy, there's other solar systems that are still just in the process of forming, or we've been able to find them at least. Our telescopes have gotten good enough that we can actually image these things. Okay, so all these top images are different solar nebula in our galaxy. And you can see some of them are different orientations, some are like edge on looking at the disk, some are almost like looking straight down at the disk, right? That's the dust that's collapsed down, and a lot of it's gone to the center, but then we form this flat disk. Some of them have like these tails, and honestly I'm not entirely sure what that is. That might have to do with the fact that they're pushing through other things in the galaxy. So those are very nice images. This one, though, struck me particularly as being pretty cool, actually. I thought this was just an artist rendition at first. This is an image taken by, what is that, the Atacama Large Millimeter Submillimeter Array. So it's a microwave telescope, or looking at the microwave portion of the electromagnetic spectrum, right? And we're able to image this solar nebula like in the process, and you can see the rings that are sort of being carved out by these protoplanets. Right? So once the protoplanets form and there's still a bunch of dust around, then they're just sort of picking it up. And there's some thought that, like, they almost act as like Swippers. They like go along, they just start pushing through all the gas, and maybe they're going faster than the gas, and they start to just like collide and pick it up as they go along. Right? But you can actually like sort of see the rings of like where planets are forming. Really cool. The microwave portion of the spectrum is really nice because in the visible spectrum, you probably couldn't see any of this stuff. There's a lot of dust and gas all around it going on right now. So visibly, we probably wouldn't be able to see that much detail, or like these sort of carved out areas. These are just a few other things that I wanted to mention as well. For one, this sort of issue might come up over and over again throughout the semester, in that, like, I might say something, but hopefully you know that that's a very simplified version of the thing, right? So when I said earlier in the slide that the sun ignites and then it blows off most of the excess material, right, out of the solar system, or at least into the belts or the clouds around the solar system, that's a very broad statement. There's still a lot of stuff that was left in the solar system after the sun ignited. It turns out it was still quite a violent place for a decent while, right? There's still a lot of things colliding, a lot of stuff happening, probably even other protoplanets that were still around, right? So things that were almost planets, but weren't quite there yet and aren't here now. So something happened to them, probably having to do with some of these oddities that we see in the solar system. One of them is, like I mentioned earlier, Venus's rotation on its axis is opposite the others, and it's very slow. the thought is that it actually was impacted by another protoplanet at some point, which kind of reversed its rotation just enough, right? So it's going in the opposite direction now, but it takes a long time. It's like 200 and something Earth days, 250 Earth days or something like that for Venus to go around once. And it's going very slowly in the opposite direction from the rest of the planets. We'll also see a little bit more about Mercury later. Mercury is like very high metal content. Most of the mass of Mercury is like this metallic core. Right? And it's just kind of odd compared to the other terrestrial planets. So it's thought that some sort of impact in the early solar system probably stripped off a lot of the crust and like so the outer layers of Mercury. So you're kind of left with this really high metal content. As we'll talk about in the next lecture, maybe, I think, the current sort of prevailing theory of how the moon, or how our moon was created at least, is an impact of this, one of these smaller sort of protoplanets with like Earth in the early solar system. Right? So this impact sort of took off some of the Earth and it was still kind of gravitationally bound, so you get all this stuff that kind of gets together and eventually clumps together and forms the moon, and we have the moon and the Earth system then. And there's generally just a lot of stuff still flying around, even though most of the stuff was thrown out. A lot of stuff's still flying around, and one of the ideas as to why, like the Earth actually has a fairly decent amount of water, of H2O, and some other lighter elements, also has to do with the idea that it was still very chaotic sort of in the early solar system, and things like comets were sort of being flung around through the solar system still, and so we got impacted by some of these icy bodies, which deposited most of the water that we now have. Last sort of extra bit here, just pointing out that we've observed now other solar systems where there are these large planets mainly composed of gas like Jupiter, but they're in the inner solar system, where they're close to the sun in those planetary systems, in those solar systems, which is confusing for our model at least, because the way I've described it and the way we generally sort of think about it is that those are going to form more towards the outer part of the solar system, further away from the sun. So those things have been called hot Jupiters because they're close to the sun. They're much warmer than our Jupiter, but they're close to their star, I should say. Yeah. So it's still kind of confusing. The current thinking about that is that due to this sort of still chaotic nature in the early solar systems, or during like the sort of formation time still, that these Jupiters, or these gas giants, these large gas planets, could form like further away from the sun, but then somehow end up getting pushed closer to it. Call this like planetary migrating. And some evidence that slightly kind of supports the idea is that these hot Jupiters that we found, most of them have fairly high eccentricity, at least relative to like the orbits that we're used to in our solar system. So remember, eccentricity is just a number from zero. We're only thinking from 0 to 1 that says like how squished the orbit is. And all the planets in our solar system are fairly close to 0. They're like 0.01 or even less than that maybe. So that means they're pretty circular, right? Their ellipse is a little bit because they're squished a little, but they're pretty circular. But most of these sort of hot Jupiters are higher eccentricities, meaning they have these more elliptical orbits, these more squished orbits, which is, I think from simulation-wise, like it seems more likely that those orbits come about not during that first formation, right? During the first formation, you tend to get these more circular things, but if stuff has to move afterwards, or is forced to move afterwards, then it might land in this more elliptical orbit. So that's the idea, at least with this. Last couple of things to say for this lecture, just to bring back the fact that this is how we think the solar system formed. We also have some pretty good evidence, namely that we see a lot of these solar nebula when we look out into the galaxy. So it seems like a pretty regular process. And I've mentioned before that we use computers a lot of times to simulate our models and try to like play them out and see how they work. And this idea, this kind of general concept, seems to work very well to produce the solar system we have today. And then the last interesting fact, I mentioned at some point earlier that Jupiter might have actually been fairly close to igniting and becoming its own star. It wasn't quite mass enough, so we didn't get that. But from sort of the census, or looking around at the planetary systems, it seems to be that only about half the time do planetary systems end up with one star. So that's like us. We only have one star, we have the sun. The other half of the time, you get 2, 3, or maybe even more stars. Yeah. I'm not sure what the term for 3 stars is, but 2 they call like a binary system, trinary system, I don't know. Anyway, it's just an interesting thing that our solar system having 1 star is fairly regular, but it's also kind of usual to have more than 1 star too. And this is some observational data of a triple star system, right, with 3 stars. And once you start thinking about more than 1 star, the arrangements, I almost put on like a bunch of pictures of different kinds of arrangements of binary systems. It can get kind of complicated. Maybe it's too much. But just to mention that, like, you could end up with 2 stars that are pretty similar mass. There's multiple ways they could orbit each other, right? They could be going in like a circle around each other. They could be going in like 2 circles, sort of opposite, interacting like that. They could have different masses. One could be much larger than the other, and the really small one could almost basically just orbit the big one. So there's a lot of different ways that multi-star solar system could end up being, right? But this is actually data like, I think there's, like I said, there's 3 stars here, and one of them I think is much more larger than the rest. And this is basically just watching the main star, and then there's actually 2 other stars that are there that are orbiting around. So see how they go around and block the main one at times. And yeah, cool stuff. So there you go. That's basic overview of solar system formation, planetary formation. I think next time we'll start talking about some of the planets, Earth and some of the other terrestrial planets, and keep at it. So I will see you then.